So this is part 2. We've done absolute value equations, and now we're going to talk about absolute value inequalities. So let's take a look at these two situations. We have the absolute value of some number is less than or equal to 4. On a number line, it would look like this. Here's 0. This means that the distance that x is from 0 is less than or equal to 4. So it could be 1, 2, 3, 4 units to the right, or it could be 1, 2, 3, 4 units to the left, or anything in between. So we're talking about something that could be negative 4, or that's negative 4 there, or positive 4 on this side, or anything in between. So as an inequality, this would look like this. We would have x could be less than or equal to 4 and greater than or equal to negative 4. Now, if it looked like this, if we're talking about n, well, n is the distance from 0 on a graph that's greater than or equal to 4. So if we go 1, 2, 3, 4 units to the right, it could be 4, but it could be anything greater than 4. Or it could be 1, 2, 3, 4 units to the left, or anything further away from 0 than that, which is in this direction. So this is a lot different of a graph. This is going to look something like this. This is going to be x is greater than or equal to 4. That's this part here. Or it could be that x is less than or equal to negative 4. So here we have a conjunction that's an or. It could be in this part of the graph or this part of the graph. Here it doesn't say it the way we've written it, but we could write the same thing like this. We could say that x is less than or equal to 4. That's this part. And it has to be x is, if I read it from right to left, x is greater than or equal to negative 4. So it has to be both. It has to be less than 4 and greater than negative 4 to be in that set. And so the conjunction that we're going to use is an and. Well, how do you tell by looking at the inequality that's if it's an and or if it's an or? Well, the key is which way the sign is pointing. If it's less than, if the absolute value is less than a number, it's going to be an and. And if it's greater than a number, like here, if it's greater than a number, then it's going to be an or situation. So, and we're going to have an infinite number of solutions regardless of what this is like, unless we have it's less than a negative number, because we can't have an absolute value that's less than 0 or less than a negative number. So let's just take a look and see how this applies to two different situations. Let's start by taking a look here at number 5 and solving this equation just like we did with the equations. First thing we're going to do is isolate the absolute value by dividing both sides by 5. And so I'm going to divide both sides by 5. My pen's getting kind of sticky here. So I'm going to divide both sides by 5, and what I'm going to have is the absolute value of 2x minus 3 is less than 7. Well, now it's a less than, so it's going to be an and situation. So I'm going to write it like this. 2x minus 3 is less than 7, and it's greater than negative 7. So what you notice is that not only does this sign, the inequality sign, switch, but the 7 becomes a negative 7. And I'm going to continue to solve this equation. If I add 3 to both sides, this is going to be negative 4. I'm going to have 2x over here. If I add 3 here, this is going to be 10. And if I divide everything by 2, I'd have negative 2 is less than x, which is less than 5. And so what you're going to see here is a graph that goes from negative 2 to 5. It doesn't include negative 2 and it doesn't include 5. It's less than 5 and it's greater than negative 2. If we were using interval notation, we would write it something like this. It would go from negative 2 to 5, but it would not include either one. So that is the first example, and that's a situation where the absolute value is less than a number. Well, number 6 is a little bit different. The absolute value here is greater than negative 12. So I'm going to still isolate the absolute value just like we did before. I'm going to divide both sides here by 2. So I'm going to have the absolute value of x plus 5 is greater than or equal to 6. But because the absolute value is greater than 6, I'm talking about distances from something that's greater than 6. So that means I'm going to use an or. X plus 5 could be greater than or equal to 6. Oops. Could be greater than or equal to 6, or x plus 5 could be less than or equal to negative 6. And so I have two different situations going on here. If I take a look at the first part and I subtract 5 from both sides, I would have that x is greater than or equal to 1. And then on the right equation, if I subtract 5 from both sides, I would have x is less than or equal to negative 6 minus 5 is negative 11. So here my graph would look something like this. Here is negative 11, and here's 1. It's greater than or equal to 1, so it's a closed circle here, and it's to the right, because it's got to be greater than that, or it could be less than or equal to negative 11. So here's negative 11, it could be less than that. And if I was using interval notation, it would look something like this. It could go from negative infinity, that's an infinity sign, negative infinity to negative 11, and it would include negative 11. And I would use the union of these two sets, or it could go from positive 1 to positive infinity. And it would never get to negative infinity or positive infinity, and that's why I use the parenthesis symbols, and then the brackets are because we have closed circles here, and it includes negative 11 and positive 1. All right, so how does this apply to anything that we would do in our life? These answers are not correct. Take a look at number 7. Specifications for a circumference of a regulation basketball is between 29.5 to 30 inches. So it could be as wide, the circumference could be 29.5 inches or 30 inches. So there's some variation in there. But how far can it vary before it's too small or too big? That's the question. So we're going to write this 3 different ways. And the first way we're going to write this is simply with a compound inequality. And so we would have something like this. On a number line, it would look like this. Here's 29.5, and here's 30. And we would say it can go from 29.5 to 30. And I would say that it can include 29.5 and it would include 30. So the way we would write this as a compound inequality would be something like this. The circumference, I'm going to call it x, could be greater than or equal to 29.5 and less than or equal to 30. Well, let's write it a different way, using plus and minus signs. And this is where I want you to start seeing here. We would want it to be right in the middle. That's what the best basketball would be, right in the middle of 29.5 and 30. Well, that's 29.75. You can find that by averaging those two extremes together. Right in the average between 29.5 and 30 is 29.75. So we could do this. We want the basketball to be 29.75 inches plus or minus 0.25. Because if I added 0.25 to that, I'd be right at 30. If I subtracted 0.25 from it, I'd be right at 29.5. So this is how we would write it with plus and minus signs. But we can also write this with an absolute value inequality, which is what we were just talking about. And it would look something like this. We'd have the absolute value of x minus what we want in the middle. What we want it to be is 29.75. But we can give or take. We can be 0.25 away from that, either to the right or to the left. Why does this work? Well, it works because what we just talked about in the last slide. If I'm going to write this inequality, I would have x minus 29.75 could really be less than or equal to 0.25, and it could be greater than or equal to negative 0.25. The reason we wrote it this way is because it's a less than. And so we changed the sign and we made it negative. And now if I add 29.75 to all 3 sides, over here on the left, 29.75 and a negative 0.25, well, that's 29.5. 29.5. And over on the right, if I add 29.75 plus 0.25, I'm at 30. And you can see this is exactly what we have here. And so as an absolute value inequality, this is the number that we want it to be. That's our target. This is called the tolerance, because how far away, it represents how far away we can be from what we want. And so that's why this is called a tolerance situation. Well, how does that apply to something like number 6? We want to write the following as a tolerance, it's a tolerance problem as a single variable absolute value equation, or inequality really. So you have a bicycle tire and it's supposed to be 113 inches, give or take a ½ inch. Well, the way we would write this as an absolute value inequality would be something like this. X minus 113 inches. That's going to move it 113 inches to the right. That's what we want it to be. But we would be okay with a ½ inch too big or a ½ inch too small. And that's the tolerance question. If we wanted to rewrite this, we would, because it's less than, we would say x minus 113 could really be less than or equal to a half. I'm going to call it 0.5, or greater than or equal to negative 0.5. Then if I added 113 to all three sides, this is going to be 113.5. And on the left, I'm going to have 112.5. And that's what we're talking about here with this tolerance. So we can write tolerances with absolute value equations. And there's actually several situations if you work in a factory where you have to set things up to make sure that whatever you're building meets a certain requirement. Well, you can plug in the numbers or plug in the data here and make sure that it satisfies this equation. And if it doesn't satisfy the equation, whatever you're building would have to be thrown out because it doesn't meet the specifications of what it is that you're putting together. That is a lot about absolute value equations. These are the 2 videos. This is part 2. And now you can go ahead and work on your homework assignment. And we will see you in class.